Good afternoon, Portland. Woo! How's everyone doing this afternoon? Sweet. My name is Yunong. I'm a software engineer at Netflix working on the Node platform. And I'm really excited today to be talking to you guys about how we debug Node in prod. So a quick backstory on Node and Netflix. By the way, for any of those of you who are interested in detail about this topic, please come check out my colleague Kim Chott's talk tomorrow. She's going to be walking you through our Node and Netflix. It's going to be really great. But we've got 65 million subscribers, and our website today runs entirely on Node. And we've also got a dynamic asset packager that runs on Node, and that serves out our JavaScript and CSS assets for the website. And very soon, it'll be serving out the assets for all of our clients, from TV to Xbox. And we're really excited about building our next generation data access layer on Node. We're sort of designing as a platform as a service framework with Docker containers and Node all together. So really exciting, lots of things going on with Node in prod. And so we use a lot of Node, right? And we have a lot of experience debugging Node in prod, and analyzing production state is really important to us. So we'll take a quick segue and let's talk about another scenario where this was important. Anyone familiar with this? So this is the Apollo 13 service module. For those of you who don't know, it went halfway to the moon and it promptly blew up with astronauts on board. And the folks at NASA at the time also had to solve stuff in production in real time, and we have some of the similar issues. And whenever we have production issues, I'm always reminded of this quote from Gene Kranz, who was the flight director on Apollo 13 for when the crisis happened, and it's really around working the problem, and let's not make things any worse by guessing, right? Because had they guessed back in the 70s, those astronauts wouldn't have made it back home to Earth. And so what does that mean, right? Apollo 13 had a crisis in production, and we want to apply the same methodology that they use, which is using the scientific method to our production crisis as well. So that involves constructing a hypothesis, collecting data, analyzing the data, and seeing if you can draw a conclusion from it, and if they don't match up, then repeating the process. And so today, I wanted to talk about 3 production crises that we've had in particular. One is on runtime performance, second one is on runtime crashes, and the third one is on memory leaks. So let's get right into it, runtime performance, right? Generally speaking, this is what folks see when Netflix is quote-unquote slow. And we want to use the scientific method, right, when we have performance issues with our site. And so one of the key things is we want to gather the request data. So we use a framework called Restify. And just like Apollo 13, it provides data for us to observe the characteristics of our app. It's built for observability. And so what it gives us is really nice audit logging around, for example, the latency of our request. So I can see a particular request here took 1,400 milliseconds, but I can drill down and see each of the requests, the handlers in that request, and see which ones were taking all of the time. And so it looks like here we have 2 handlers, parse, body, and render, which are completely on CPU, taking 1.1 seconds, right? And as many of you know, CPU is really, really critical when it comes to Node apps, because Node is essentially single-threaded. And if we were in a threaded world, we wouldn't block everything else from executing if we were on the CPU. But in the Node world, because we have that one evented thread loop, everyone gets a turn, but if a piece of code is on CPU for a very long time, it has this cascading effect on everything else in the system. And so we don't know which requests are slow, because since if there's just only one bad actor, it has this negative impact down the line, right? And so with this case, we've got this data now. We know that, hey, I think we're spending 1.1 seconds on CPU across this one request. But how do we relate this back to our source files, right? How do I go relate this back to all of the code and sort of try to fix what's causing the CPU issue that we think is a CPU issue? Well, we could do this by hand, right? Let's inspect the code manually. Well, that seems like a bad idea. We've got 6 million lines of code, right? Which includes all of our Node modules. And we want to be able to find the specific lines of code that's actually causing our CPU, for us to spend all this time on CPU. So one technique we could use is to statistically sample our stack traces. Right? We're seeing the spinner. We figured out that we think it's not networking, but we can't simulate this stuff offline because we don't have the production traffic patterns. So one thing we can do is use stack traces to snapshot what we're currently executing. Right? A stack trace is a really great way to see exactly what is running on CPU at a particular point in time. But we were kind of running into 2 problems here. Right? One of them is, well, how do I sample stack traces from a running process, right? And then the second problem, which I think is even more important, is how do I do that without affecting the process? I mean, I could do console.trace or attach a debugger, but doing that in prod means that we're effectively pausing the process or adding unnecessary performance issues in addition to the ones we already have. So what's really great is there's this framework called Linux Perf Events, and it's this great dynamic tracing framework that lets you sample the CPU for any process within Linux. And so here we can actually sample stack traces with perf in Node. So we're using perf, and we're sampling our Node process at 99 hertz for 30 seconds. And you can see that we've taken about 23,000 samples. And here's what an example stack trace that we would get from perf events will look like. So you can see the things in blue, that's our V8 stack frames. The ones in red is libv, and the ones in yellow is just libc. But what's conspicuously missing is our JavaScript stack frames, right? If we want to apply the scientific method, we want to gather all of the data. We don't want to just shoot in the dark, and we really would like to get those JS frames. So why don't we have those JS frames? Well, it's because, as many of you know, V8 places the symbols just in time, and so those addresses change all of the time as well. But really, what's really nice is in the latest versions of Node and V8, there's this flag that V8 provides called perf basic prof only functions. And what this does is it outputs a translation file in a format that perf events expect. So you can translate those native frame pointers to JavaScript stack frames. And you can basically run this in production forever because it's very low overhead, and the file that it outputs is very small. And it's available right now in 5.x, so those of you that have it running on Linux can try this out right now, and it's coming soon to 4.3. Do some great work. Alicia and Jason Snell have been doing out of the LTS working group to try to backward this. And so what this results in is actually both JavaScript frames and native frames in my stack traces that I'm able to statistically and dynamically sample from my production application. But again, then we run into sort of this big data problem. Right now we've got all of our stack traces, but now we have too many of those, right? We have 744 stack traces, and we've got over 58,000 stack frames. And so if we were to visualize this, if I were to print out every single stack trace that I would get, it looks like that, right? So I don't know, I can try to inspect this and try to figure out where I'm spending all my time on CPU, but gee, it would be nice if we could visualize this. And so there's this really elegant solution that a colleague of mine developed, Brendan Gregg, which is called a flame graph. And this is what that looks like. And we're going to walk through this in detail. So each box in the frame graph represents a stack frame or a function in the stack. And the y-axis is the depth of the stack, right? And it shows you ancestry information. And the x-axis is the percentage of time you spend on CPU. So it doesn't show the passage of time, but it shows you how long each function or its ancestors spent on CPU. And then the colors are generally random, but in this case, I've colored them to make it easier to disambiguate. So you can see the red frames are libc, and the yellow frames are V8, and the blue frames are built-ins, and then your code that we've all written is in green, which is probably what's slow most of the time. And so to improve performance, we can also grab low-hanging fruit of any frame that's spending a lot of time on CPU. So if we were to drill down a little bit into flame graphs, we can sort of walk through a simpler example to see if we can better understand them. So, as we all know, the top edge, like I discussed earlier, shows you what is running currently on CPU and how much. The width indicates how much it's been running. So we can see that in this flame graph, the functions E, G, D, and I are all running on CPU, and G is by far taking up most of the time. And then as we drill down, the top down shows our ancestry. So we know that G derived from F and D, C, B, and A. And then if we look at the widths are proportional to its presence in samples. So the wider a frame is, the longer it's spent time on CPU. So in this case, we can see that B spent a lot more time on CPU than, say, H. And so that's where it matters a lot, because we want to take the lowest hanging fruit, right? So we want to take the code that spent the most of the time on CPU and optimize that, because that's going to give you immediate, noticeable, and gains to the performance of your application. So if we go back to a real-world example, this is a flame graph we took of that application that we thought was slow. And we know that each individual flame corresponds to a code path in the application, and the widest path represents the code path that spent the longest time on CPU. Right? So let's focus on the widest frame, which is this one right here. And if we start from the bottom up, we can see that, hey, I'm spending 50% of my time in this function called profiles_gate. And this is the little profile that you see up on the top right corner of your Netflix app. And it's interesting because this is the app that renders the entire website and all of its pages. And the profiles_gate is a very small portion of the website. And in fact, it's rendered on the client side. So why would we be spending 50% of the time on CPU? Well, if we scrolled up into the stack trace, into the flame graph, we can actually see its stack trace. And we can see that, hey, we're spending 99% of what's in profiles gate in Lodash, right? So we would not expect this. Actually, this is a good place to stop, because immediately from looking at the flame graph, I'm able to pinpoint within that 6 million lines of code where I should start investigating and looking to see where I can get my performance wins. And so if we investigated that line of code, we see that it's merged. We're using function lodash.merge, which recursively merges all the properties of two objects. Now, this was a silly programming error, because really what we wanted to use was assign, which only merges the top level properties. But as you can see, like something this trivial and benign, which is caused by a silly programming error, actually caused a huge performance issue for us. And with flame graphs, we can easily visualize that. And so if you look at the before flame graph with a really wide stack frames for Lodash and compare the after, we can see that that entire flame has just now disappeared. So now we're no longer spending any time really on CPU doing profiles gate. It might be like that tiny sliver out to the side somewhere, but now we can repeat this process and start with the next widest frame. So flame graphs really helps you find that one line of code out of the 6 million that you've got to optimize your performance. And for us in this case, it resulted in dramatically reduced request latency across the board, reduce CPU utilization, and increase throughput of our app. And so in terms of that runtime performance technique, you want to sample your stack traces with perf. You want to visualize that distribution with CPU flame graphs, and then identify candidate code paths that you want to optimize, improve, and try to improve those, and then repeat the process to gather more data, right? So back to that scientific method, always repeat, and always try to gather data first and try to draw conclusions from your data. So let's move on to the second topic, right? Runtime crashes. I'm sure we've all had these where our code just blows up. And in fact, NASA also has these problems, right? It sends probes and spacecrafts all over the solar system. And so it turns out there's a paper that they published in '71 where for their probes, right, if they're flying past Pluto, you only fly past Pluto once, right? If your probe is crashing, what they want to do is save all of that state in the form of a core dump, restart the probe, and continue to gather data. Because again, you only fly past the planets once, and you want to gather as much data as possible. And so we want to do that as well, right? And so let's go into a brief history about core dumps. It actually derives from this magnetic core memory that they used to have back in the day. This is way beyond my time. Engineers used to dump out the contents of the core memory onto paper for debugging. So that's why it's called a core dump. And these days, we were able to dump the core, the core dump onto the file system. But with the event of the core dump, postmortem debugging was born, right? And so when we have a production crash like this, we have some of the same characteristics as NASA, right? We want to uptime is critical for us. We want you guys to enjoy the great, awesome content that we have. Some of the problems are not easily reproducible given the large number of subscribers that we have, and we can't simulate this environment, and we want to resume operations. This is where postmortem debugging is really great, because it minimizes downtime. Just like the NASA use case, I can take a core dump and then immediately restart my app knowing that I've captured all of my process state. And so now I can continue to serve traffic, and in the meantime, load this core dump up somewhere else and debug it there at my own leisure and engineer a fix, right? There's no need to pause the machine or process, because we can snapshot the entire state of the app. And in fact, you can easily configure Node to dump core on error. This flag has been around for a very long time, abort on-call exception. And if you start your app with this, anytime there's an on-call exception that's been thrown, Node will exit, but in addition to exiting and dumping out the stack trace like it normally would, it will also generate a core dump which captures all of your process state. So let's spend a moment to talk about sort of the Node postmortem tooling that's available out there. As many of you know, we run, Netflix uses Linux in production. And in Linux, there are some tools out there that are works in progress. They're not completely feature complete, but they do exist. But at the same time, there exists this other fully featured tool on Solaris called MDB v8, which is compatible with Linux cores. And so core dumps are valuable, right? And for us, when we have a crash in production, we needed to engineer a patch so that we can actually get back up to speed, right? So like if we were stuck in space, here's our example. We need to MacGyver something together to get everything up and running and fix our problems. And it's worth noting here that this is the carbon dioxide scrubbers from Apollo 13. So when the service module blew up, they all had to move to the lunar module, which is designed for 2 astronauts and not 3. And so they quickly ran out of the carbon dioxide scrubbers in the lunar module. They're like, oh, great, we'll just use the ones from the service, from the command module. But it turns out that in classic fashion, you can't make this stuff up. The lunar module's canisters were round, and then the command module's canisters were square. So they literally had to use some duct tape socks and paper and plastic bags to engineer like an adapter to make this work. And so this is sort of what we're doing too, right? We We've got Linux core dumps. We would like to analyze them, but the Linux tools aren't feature complete yet. So our stocks and duct tape solution is to set up a debugging Solaris instance. And that's also the beauty of postmortem debugging, because I don't need to actually debug this stuff in production where my code lives. I can save the snapshot and debug it somewhere else. So let's walk through some of the postmortem methodology, right? I want to figure out where and why. So where did my app crash? And I can do that by inspecting the stack trace. And why did it crash? And I can do that by inspecting the heap and stack variable state. And so here are some of the MDB commands. The most important one you want to remember is help, because it allows you to read the man pages for all of these other commands. So if we quickly, we can load the core dump here on a Solaris instance by passing MDB, the Linux node binary, and then the core dump, and then we can load the MDB v8 module, and then we can immediately inspect the stack state by using the command jsstack. And you can see here it gives us both JavaScript frames and native frames, and we can even see the function names. Now, what's curious is a lot of these functions are anonymous, and I'm about to rant a little bit, but we should always name our functions, right? Because if you name your functions, it means that like at 3 a.m. in the morning when you're debugging a production crash, the DevOps guy and you are able to see the names of these functions, both on the stack, which makes it helpful, but also on the heap. It's impossible to find, it's really, really hard to find objects on the heap if you don't know their names or if they're anonymous. So always name your functions. It'll really help you when you're trying to debug production crashes. But back to JSStack, I'm even able to get see the source code for each of my stack frames in my stack, which is really helpful, all without having access to my source code. And this is good for operators who may not have the source handy. And then additionally, I get the function name, the JavaScript file that it came from, the line number, function arguments, which is really helpful, because most of the time we're able to get the stack, but you really want the additional state of what variables were on the stack that caused you to crash. And indeed, we get the memory addresses of all the variables on the stack and the types. And then we can actually print out all of these variables using the jsprint command, and that gives us an actual JavaScript object instance. And so now with both the stack trace and stack variables, you have more data to try and solve your problem, right? Additionally, you can print out the constructor of any object that's available. So here I'm passing an address to a JS constructor, and it gives me a JS function address. I can actually dump out the source code for that as well. So all of this is really helpful because the core dump then gives me this complete process state, right, of not just what's on the stack, but all the arguments and the variables, and all the variables on the heap. And this really helps me gather all the state that was in the process before it crashed, so I can try to easily reproduce and fix the issue. So let's move on to our last problem, which is memory leaks. Has anyone hit memory leaks before? If you don't have your hands up, you're probably lying, but it's cool. We'll let that one pass. Like everyone else, we occasionally get memory leaks, and it's the stuff that nightmares are made of. The build on the left is the new build, and you can see the memory is just rising and rising and rising, right? And people are freaking out. But for a lot of you who don't know, we actually have a secret weapon up our sleeve when it comes to memory leaks. It turns out our CEO, Reed, in his previous life at Pure Software, was actually an expert in memory leak detection, right? And so whenever we have a memory leak, this guy shows up, and we're good to go, right? So you might not have Reed, and for me to call in Reed every time might be a little bit career limiting. So let's sort of see if we can use some of the techniques we just showed earlier from the previous section. Maybe that'll help us debug our memory leaks. So what we want to do now is we want to be able to generate core dumps ad hoc, right? So not just when an app crashes, but whenever we want, because when you have a memory leak, you want to be able to just take a core dump and have the app continue to run. And so a great tool that already exists on all of your operating systems, all of your Unix and Unix-like operating systems is gcore, and that generates a core file for any running process. And so it's really, really fast. It's an OS construct, and it captures all of the information, again, as part of the core dump. So here I can just take a quick core dump of my node process in production, right? And then anytime I want, I can do this, actually, with just quickly interrupting the process, take a core dump, and the process will continue to resume. So now we have a problem, right? Our problem is that we want to find the objects that are leaking as part of our memory leak. And so a really great command that comes from MDB v8 is find JS objects. And remember, all the other tools we discussed earlier are still available, but what find JS objects lets you do is find all of the JavaScript object on the heap, every single one of them, right? And so you can see here, if I just run this, the first column gives me an address of the representative object. The second column gives me the number of objects. The third column gives me the number of properties, and the fourth column is the constructor with its properties. And so our memory leak strategy then is when we have a memory leak, we want to look at all the objects on the heap, right? And maybe we want to look for like suspicious objects. Like if I have 500,000 buffer objects, that's probably suspicious, and that might be something that I'm leaking. But we can also take successive core dumps and compare object counts. Because if we do that, then if there are any objects that are consistently growing, then those are the objects that are probably leaking, right? Growing object counts are sort of what really is causing, could be causing your leaks. And then we want to be inspecting that object for more context, and we can then walk the reverse references to find the root object that's holding on to the references to these leaked objects. And with this methodology, the tooling is safe to use because it's postmortem debugging. So once you take a core dump, you're off that production instance, and you can look at it to your heart's content and do whatever you like. And so let's look at object deltas between successive core dumps, right? Here I've taken a core dump at 45 minutes, and there's a suspicious set of objects called the module object, and I have 230,000 of them. And it's kind of weird. We all know that Node caches its module objects, so have I really required 230,000 different versions of modules? That seems unlikely. But let's use that scientific method. We think that's what's leaking. Let's take another core dump 90 minutes later and see if it's growing. And in fact, it is. So we see now that it's grown up to 323,000 objects. So great. Now let's see if we can analyze this object, right? So we want to analyze the leaked object and use the scientific method. So we can grab a representative object. So remember that there's 323,000 objects. So MDB will find JS objects will give you just a representative object. And if we look closely at just this object, we've already gotten a lot of value, right? Again, out of that 6 million lines of code, we can see that, hey, here's a module, what looks like a module metadata object, and the module itself is something that's inside of our app. But let's look more closely, right? We can actually use find.js objects to find all the module objects. You can actually pipe find.js objects back into the memory address of any object, and it'll dump out the addresses of all of the 320,000 objects. Now, I feel like I sound like a broken record, but again, we've hit this big data problem, right? I have 320,000 objects. It's going to be really, really hard for me to analyze all of those by hand. But we can use Unix tools. MDB supports for you to go shell out and pipe out to the shell. And we can use Unix tools to get a distribution of the modules by their file names. And that's what we're doing here with this Unix one-liner. And that returns a set of results. And we can see the things highlighted in red here, hundreds of thousands of modules that we think are being leaked. And what's even more damning is that these modules are things that we own. And even worse, they're client-side modules. They shouldn't even be loaded on the server whatsoever. So this is really great, right? It's strictly narrowing things down to like our code, the specific modules that we're looking at. And but now the question is, what's holding on to all of these modules, right? So now our aim is, well, let's find that root object. And you can do this by finding reverse references with find.js objects-r. So through recursive iterations of this, you can actually find parent objects that hold on to references of whatever object you're looking at. And eventually we get to the root object, which looks like an array internal to Node, which holds on to references of all the modules that you've tried to require in. And so we've gotten a lot of data now, right? We know that all the modules that we think we're leaking are modules that we own that are client-side only. And we know that they're being held on by an internal Node data structure that holds on to references of any module that you've imported. So when we go inside our code, we can find the spot where we're requiring these modules. And it turns out that we were abusing the module loader. Because we run universal JavaScript on both the server and the client, sometimes we need to grab state from these modules, and so we load them in. But on the server, we don't want our app to crash if we're requiring a client-side module, right? Because it might refer to window or something. And so we try and catch our required, you can see here. And if it blows up, we catch it and return nothing. But what we forgot to do here, though, is cache the fact that we already tried to require in this module. So the root cause actually happened was that no caches metadata for each module that you import. If your require process throws an exception, then that module metadata is leaked within Node. So this could be a bug in Node, but we're really abusing the fact that we're requiring modules and catching them. Nobody would actually really catch a require statement. And usually the process would exit and you get a new clean state. Because we were abusing this fact and not caching the fact that our client-side modules were throwing, then during every request, we will leak like 3 or more of these module objects. And so that's what ultimately causes our memory leak. And with the memory leak technique, which is take successful core dumps, compare our object counts, check that the growing objects are probably the ones that are leaking, and then inspect the object for more context and walk their reverse references, we're able to fix this leak, right? And I think this is something that's really helpful for us whenever we have a memory leak. And indeed, postmortem debugging is really, really critical to us when we're running our large-scale prod node deployments, right? Because we can't have an off day ever, right? If we have an off day, people can't enjoy the content. And so what postmortem debugging gives us is more state than just logs, right? You get basically everything that you want about the state of your app. You get your stack trace, you get function args for each of the frame on the stack trace, you can get the state of any object you like and its provenance, you can get source code for any function, and you can find arbitrary numbers of JavaScript objects. But what's really important is that it requires zero modification to your node binary, right? I'm not running any additional modules or any other runtimes. I'm just running node by itself. So in summary, we know that production failures are inevitable, right? Both in space and at Netflix, but we can learn from them. And by analyzing core DOMs and root-causing failures, we can ensure that we don't hit the same problems over and over again. And so today I talked to you folks about production debugging. When it comes to runtime performance, we use CPU profiling and visualizations via flame graphs. For runtime crashes, we can inspect the program state with core DOMs and MDB. And for memory leaks, we can analyze references with core DOMs and MDB as well. We didn't bring back astronauts from space by guessing, and we shouldn't do that in production either, right? And lastly, use the scientific method. It's something that you should always start with when you're trying to debug a problem. And now a quick epilogue on the state of tooling. If you're at all interested in postmortem debugging, you should join the working group, contribute. Help make MDB V8 cross-platform. It's an open source project. And then also contribute to the various Linux efforts that are out there too, and make them more feature complete, right? Remember the socks and duct tape patches? Help make this better, right? And I want to acknowledge all the fine folks who spent a lot of hard work to make all these tools available so that we're able to run Node in production at scale. And lastly, get involved, right? You guys here are all part of the community. So help drive these tools forward by using them, sharing the knowledge, contributing to them. Thank you very much.